This dimensional analysis example involves volume, which follows the same general principle as linear measurements such as inches to miles and such. There are different types of dimensional analysis involving volume that you have to watch out for, but this one is kind of a two-part dimensional analysis problem that is a little bit more involved. This example asks, convert the volume of this rectangular prism into cups. So this is a three-dimensional figure. It has three dimensions like length, width, and height. And the first thing we have to remember is how to find the volume of a prism. The volume of a rectangular prism is the length times the width times the height. And when you find the volume, in this case, it would be 5 times 4 times 6. And I know that's 5.0, 4.0, and 6.0, but it's 5 times 4 times 6, which happens to be 120 cubic centimeters. When you have units such as centimeters or some other length, and you multiply it by itself twice, you get a square unit, such as centimeters squared. If you have a unit and you multiply it by itself 3 times, you would get a cubic unit, which indicates volume. Three-dimensional. So our thing, what we know, is we've got 120 cubic centimeters. That's how much space this rectangular prism occupies. I'm going to convert cubic centimeters from cubic centimeters into somehow cups. And this is where we have to think about what our conversion factors are, what is provided to us, what we know off the top of our head, and what we could reference, and how to connect cubic centimeters to cups. So let's take a look at our conversion factors that we have here. 1 cup is 8 ounces, and 1 ounce is nearly 30 cubic centimeters. It would make sense that for me to go from cubic centimeters to cups, I would first go to ounces and then cups. So cubic centimeters connected to ounces is 1 ounce, which is relatively large compared to a cubic centimeter, is 29.57 cubic centimeters, nearly. It's not exactly that. If you look at your units, cubic centimeters are going to cancel top and bottom, and then I'm going to go from ounces, canceling that using the denominator position, to cups. 1 cup is 8 ounces. Ounces are going to cancel, top and bottom. Cups are not going to cancel, and when we do our math, our answer will be approximately 0.51. I'm going to actually be a little bit fancier here and put the approximal symbol, nearly equal to. And don't forget your units. We have cups. So what that effectively says is that the amount of space that a 6 by 4 by 5 rectangular prism occupies is nearly half a cup. Example 4 is asking us to convert miles per hour to feet per second. This is different from the last 3 examples, the first 2 of which were in a separate video, because this is two-dimensional. We have one dimension on top of, or divided by, another dimension. Usually these are rates, miles per hour, or feet per second, or meters per second, or kilometers per hour, some distance divided by time. A car is moving at highway speeds, about 68 miles per hour. How fast is the car going in feet per second? That is the first part of this question, and the second part is, how many feet does the car travel in 1 minute? What I know is that I've got 68 miles per hour, which is abbreviated as mph. But you're probably going to be tempted to do this. 68 mph over 1, and then you may do like, how do I cancel mph to go to, and you kind of hit a wall because you don't know the conversion factor from miles per hour to feet per second. It would be a derived conversion factor. So the way to do this is a little bit different than the prior examples have shown. Rather than putting 68 miles per hour over 1, you need to recognize that this bar here, this per, is going to be analogous to this bar here. So really, we have 68 miles per 1 hour. Your denominator is no longer just a 1 if you choose to do what I do. Your denominator now is an actual unit, 68 miles per 1 hour. Multiplication bar, and then you look at one of the two units. I'm going to do some color coding because I think it would help out a bit here. The bottom is hours, and the top is miles. I meant to do that in a different color. There we go. I'm going to deal purely with miles. I'm going to turn my miles from miles into feet, and then I will turn my hours into seconds. Deal with one part at a time, the numerator or the denominator. I'm choosing to deal with the numerator first, so let's deal with that in blue, light blue. Miles are going to go at the bottom, and we're going to do the same thing we've done in the past, go from miles to feet. And the relationship between miles and feet would be 1 mile is 5,280 feet. If you want to do the cancellation, miles will cancel top and bottom, feet will not cancel, so I will circle it. You are not done with the problem, because if you look at the units you have remaining, you would have, after doing math, 5,280 feet divided by 1 hour, so your units would be feet per hour. You need to continue your conversion factor, or your dimensional analysis problem using another conversion factor. Dealing now with the hours, knowing that my feet are done, I'm going to look at where hours was, which was here in the denominator, and I think to myself, hours was in the denominator, I need to cancel it by putting it in the numerator. Even though it is not next door, it will still cancel at a distance. I'm going to go from hours toward seconds. You may know how many seconds are in an hour, or you might know how many minutes are in an hour and do that instead. The relationship between minutes and hours should be something you know, which is why I did not list it in a blue useful information conversion factor. But hours to minutes, 1 hour has 60 little minutes in it. The next part of my dimensional analysis would be one more conversion factor, canceling minutes from bottom to top with seconds. Minutes and seconds, 1 minute has 60 seconds. I'm going to circle my seconds. It's important to really look at what's going on here. Feet is on the top. It was not canceled by anything else. It was our final destination. Seconds is on the bottom. It was not canceled by anything else. It was our final destination. And that is exactly what we want. That is why canceling out your units when you're first learning how to do this, using actual strike marks, is really helpful for understanding what is going on. Because the feet and the seconds are not actually on top of each other in the traditional way you would see it. When you do your math for this problem, you will see that your answer is approximately, and this is not regarding significant figures, is approximately 100 feet per second. Thinking about rates, that means that every second that car is driving at 68 miles an hour, it goes 100 feet. It's kind of why texting and driving, snapping and driving aren't good, because if you look down for just 2 seconds, you will have covered 200 feet. Okay, so that was part A. Part B is going to ask us to determine how far the cart travels in feet after 1 minute. You could turn your miles per hour into feet per minute, or you could recognize, and this is where the beauty of the math and science comes in, because there's many ways to do something so long as you do it correctly. You can recognize that 60 seconds is a minute. So we're going to use this problem here as part of our information. Rate equals distance over time. What are we solving for? It asks how many feet, which is going to be your distance, does the car travel in 1 minute, which is going to be your time. You have to have also the rate, which we just found, in feet per second. These are going to be approximate values. It was 99.733 feet per second. We're just going to stick with 100 for simplicity. So I tend to write the equation out again. Rate equals distance over time. And then I rearrange the equation to solve for what I want. I have the rate we just solved for. It was 100 feet per second. I have the time. The time is 60 seconds, which is 1 minute. I need to rearrange this equation to get the distance alone, and to do that I would multiply both sides by t. Multiplying both sides by t gets rid of it on the right, and then it provides me with a rearranged equation that the rate times the time equals the distance. And let's see if this is true. The rate is 100 feet per second. I am multiplying this by the time, which is 60 seconds. You don't have to put it over 1. I'm just going to do that anyways. 60 seconds divided by 1 is simply still 60 seconds. It's just one dimension. And then I should be able to calculate my distance. Looking at what will cancel within the dimensional analysis here, seconds are going to cancel bottom to top. Feet will not cancel, and that makes sense because feet is a distance. So 100 times 60 would give me 6,000 feet. So in 1 minute, which is 60 seconds of driving, the car will have traveled 6,000 feet, which is a little bit more than a mile, and that makes sense because the car is traveling 68 miles per hour.